Hello algebra students, welcome back to another video lesson with Mr. J. Today we are going to expand our polynomial work into multiplying. And we're just going to start with multiplying a monomial by any type of polynomial. So where we've got something that's got one term to a variety of terms. And so by the end of today's video lesson, we should know how to multiply these and simplify them. So it is going to be really important that you get down some important notes and some examples that we're doing. We're working out of the packet on page 4. There is a really important property that I want to discuss with you here on page 4. The generic formula looks like this. A to the power of m times a to the power of n equals what? Now, in order to understand that rule, I want to look at the examples. X to the third times x to the fourth. Well, what's a more longer version to write out x to the third? X times x times x. Okay, so that's, I'm going to just underline it. That's what x to the third is. Then let's do the x to the fourth in green. X times x. Whoops. Times x times x. There are 4 of them. What's being done with these two? Well, they're all being multiplied, right? X to the third multiplied by x to the fourth. So they've all been multiplied together. So if I've got 3 here and 4 here, that really means I have x to the 7th power. Right? The shorter version then of this longer version is to combine them. Well, what do you think happens here if I have x times x to the second? Well, this is x. This is x times x. So we really have x to the third. Right? Even though there's not anything there, it's a 1. So what do you think this property or rule might be telling us if we look at x to the third times x to the fourth, and we got x to the 7th, or if we got x to the first times x squared equals x to the third? Really, this rule is telling us if they have the same base, we can add their exponents. If they have the same base, we add their exponents. So look, x to the third, x to the fourth, add their exponents, 7 of them. X and x, add their exponents, we've got 3. So that's true when they're the same variable or they have the same base. Now, we can also look at this by looking at it in terms of a box. Notice they're asking us here to multiply 9a to the fourth b to the fifth times 8a to the third b. Whew. So it's a 1 by 1, monomial times a monomial, one side times one side. When we multiply a monomial times anything else, and we look at a box, we're going to multiply the coefficients, right? So we're going to have 9 times 8 times a to the fourth times a to the third times b to the fifth times b, right? So 9 times 8, 72. A to the fourth times a to the third. This part of the problem looks like what we just did on the previous page. They're both a and a. They're being multiplied. So we can say we have a to the 7th. We can add them. B to the 5th times b. B to the 5th times b. That's just like the other page. If I've got 5 and 1, that means I've got b to the 6th. So we're using that property along with multiplying. 9 times 8 is 72. All right. See what you might get for this second one. I've got 1/2 times -6. So that's -3. So let's just put that in the box. G squared times g to the third. G squared times g to the third. Well, they're the same base. They're both g's, so I'm going to add. Gives me g to the 5th And then we've got h to the fourth h. 4 and 1 make 5, so h to the fifth. So again, we're multiplying those leading coefficients, and then we're going to add the exponents because they've got the same base. And this is true in this case because it's a 1 by 1. Everything is just being multiplied together in both of those examples. Now, what happens when we expand this a little bit and go to what might be a monomial times a binomial? A monomial times a bi. Well, you'll notice this side only has one element, meaning it's that x. We have three x's, so I'm going to put an x and an x and an x, and then I have a 1 or a 1. And now I'm going to do a lot of like multiplication for each 4 of those boxes. X times x, that's an x squared. X times x, that's an x squared. X times x, that's an x squared. Oops. Squared, Mr. G. And 1 times x is a 1x. And now we're going to add our like terms. We're going to add those elements together. X squared, x squared, x squared. How many apples do I have? Well, I have 3 of those x squareds. How many x values? Just 1x. So we could use this visual representation if we wanted to. If it's helpful, go ahead. This would be an x and an x. This would be an x with a -1, a -1, and a -1. What I prefer, and I'll show you this, is to use the distributive property. Right? This has to get distributed to both. And the distributive property uses multiplication. 2x times x plus 2x times this -3, even though it's a subtraction sign that goes with the 3. And now I'm going to simplify each term. 2x times x. 2 times 1 out front is a 2. X times x is x squared. Plus 2 times -3 is -6. X times, we just have to make sure we have that x. So you can use the distributive property as well to help you simplify. Why don't you try this one? Pause the video and see what you get in this example. So again, we can use this distributive idea, right? These two are being multiplied, so that's one term, plus these two are being multiplied, right? Whenever we have that plus sign, we're differentiating between the terms. So over here, we've got -3 times 4, which is -12, and x squared times x times x becomes x squared, right? I add their exponents, a 1 and a 1, plus 3 times 2 is 6, times x squared means I just still have 2 of them. Now notice, though, I have -12 of the x squareds and 6 of the x squareds. Are those like terms? They are, because they have the exact same variable with the exact same exponent, x squared. So I can add the -12 plus 6 to get -6 of those x squareds. Remember, when we add or subtract elements and terms together, we do not change the variable. Now here is what we would call a monomial times a trinomial. Monomial times a trinomial. And what might a generic rectangle look like? Okay, well, I would have a 7y squared for my monomial, and then I'd have the 3 terms across top. And this is just illustrating a little bit further what the distributive property is doing. Right? I have to take that 7 excuse me, I got to take that 7y squared and multiply it to each term of the trinomial. So times that one, times the second one, and times the third one. And so this box just shows me that, okay? So this is the cross section of 7y squared and negative 3y to the fourth. I'm multiplying. 7 times negative 3 is negative 21. Y squared times y to the fourth. They both have the base of y, so I add them. Now the cross section. 6 times 7 is 42. Y squared times y gives me y to the third. This is negative 5, so 7y squared times negative 5 gives me negative 35. Y squared, and there aren't any y's in this one to add to it, so it stays as y squared, meaning our final simplified version would look like negative 21 y to the sixth 40 plus 42 y to the third minus 35 y squared. Can't add or subtract any of those together because they don't have the exact same variable with the same exponent. All right, so in your packet, you've got 4 of them on page 4 that I'd like you to try. Okay, try those 4, and what I want you to do is make sure you bring them with you to the next live session that you're at, either today or Friday, so that we can kind of talk about them and go through them as we continue to get a little bit more and more complex each time. If you have any questions, please make sure that you reach out. Otherwise, until next time, folks, stay safe.